So in our last class we have seen that for a single degree of freedom spring mass system, which is actually a simplest type of model of an actual system. So this is a lumped model because mass is lumped and the elasticity is also lumped. Mass is lumped in the point mass, and the elasticity property, the distributed elasticity, is lumped in the spring. And we have seen that the total energy is conserved. Now suppose you have a spring mass system where the total energy is conserved because there is no dissipative mechanism here. So, and from the static equilibrium position you measure x. Now you tell me that suppose someone plots x versus t. So x versus t, someone plots x versus t. This is t and this is x. Then when x is maximum, here the velocity is 0. So when x is maximum, the velocity is 0. That means when x is maximum, velocity is 0. That means the potential energy is maximum and the kinetic energy is 0. Here. So what is? So when for this point your kinetic energy is 0, because from here the direction of the mass changes, so it must pass through the 0 velocity value. So 0, that means, and at that position the potential energy is maximum. And here when it passes through this point, the potential energy is 0 if you measure it from static equilibrium, and the kinetic energy is maximum because this is the maximum velocity point. So if you differentiate it, then the velocity will have a peak here. So here negative peak and here positive peak. So this is to when the kinetic energy is maximum, the potential energy is 0. So Tmax is equal to Umax. Tmax is equal to Umax. So this is interesting, and you know T is equal to half m x dot square. So if you take x as some x sine omega and t, then x dot is omega n x cos omega n t. So we can put it here. So half m, this is omega n square x square cos square omega n t, and T max is this cos square omega n t equal to 1 when t is T max. So this is half m omega n square x square, and you know U max is half k x square, which is half k x square sine square omega n t, and when u is U max, the sine square omega n t has to be 1. So U max is half k x square Now if you equate Umax to Tmax, if you equate Umax to Tmax, then half m omega n square x square is equal to half k x square, or omega n square equal to k by m, and from here you can get the natural frequency. So this is an interesting observation, and now we will discuss Rayleigh's method for SDOF system. Rayleigh's method. Now we will discuss Rayleigh's method. So what we do is Rayleigh's method is an approximate method by which we can reduce a distributed mass system to an approximate single degree of freedom system. And when can we do it? We can do it when the displacement at any point or the motion at any point can be expressed with respect to motion of a single point. So all the points, the motion of all the points can be expressed in terms of the motion of a single point, and that means motion of all the points of the actually distributed mass system. All the points of the system can be expressed as a function of, or as an approximate function of a single point. Or better we write expressed in terms of expressed in terms of a single point using an approximate function. So let us try to understand it with the help of this example, where see this is a spring, but the difference of, so this is spring with mass. So it is a spring, no doubt, but this is not a lumped elasticity spring. This spring has also a distributed mass, but the motion of any point on the spring, like this motion at this point on the spring, can be expressed as a motion of this single point on the system. How? Suppose the motion of this point, that is the tip of the spring, can be expressed as xlt. So xlt means xl comma t. That means some xl into t, say sin omega nt or cos omega nt, whatever. And here at any point this x at y t can be expressed as this x at y into sine omega n t. Now this x at y, the amplitude at y and the amplitude at L are related. So this is capital XL is the amplitude at L and this is amplitude at y. How are they related? That is, you have to find an approximate function by which they are related, and you have to take an approximate function which is close to the actual thing. So here if you take x at y is x at L, a linear function, into y by L. That is, here a little bit of correction here. Here suppose this is x at L, then this is x at y, which is x at L into y by L, that is divide by L into y, that is a linear function. So this is the thing. So that means the displacement at any point on this spring which has a distributed mass, suppose the spring mass is spring total mass, or total mass of spring is ms and mass of spring per unit length to ms by L. So and this you can call some function of y, and this function of y is 1 at y equal to L. When y becomes L, this function becomes 1 and xy becomes xl. So now what is the kinetic energy for this portion dy? So for dy, so what is dy? Okay, what is the kinetic energy for dy? Dt is the kinetic energy for dy is dt. So half mass into dy. What is that? That is mass per unit length into dy into length into x dot square. So that means half ms by L dy into x dot square. So x dot square means here x dot square, so this will get differentiated and this is this, so xl into y by L and then omega n cos omega n t. I think it's okay. So this is x at y and the time function is this, so this get differentiated like this. So but this is square, so this part has to be squared. So this is half ms by L. So let us do it like this: x square L 1 by L square omega n square cos square omega n t, and what remains is y square dy, and for the total kinetic energy this has to be integrated from 0 to L. So x square, okay, L square omega n square cos square omega n t and y square dy. So that is L square by L cube by 3, and this L cube goes. So this is half ms by L x square L, and if you take T max, then you this portion, this goes to 1. So x square L 1 by L square omega n square, and from here L cube by 3. So go. So this is half ms by 3, this is half ms by 3 omega n square and x square L. And what is the kinetic energy? This is only due to the spring, and if you add, so T max total, so T max total, that means if you add the kinetic energy of the mass also, that is half m omega n square x square plus half ms by 3 omega n square T max. This is T max total. So this is half m x dot square, and x dot square means here you have to take this. So x capital L capital X L omega n, here you differentiate this. So this is omega n cos omega n t. So maximum, if you take the maximum, cos square omega n t goes, so this remains, and here x square L. So this is half m plus ms by 3 omega n square x square L. And what is that? Means in place of mass you have to take this correction, this mass, where 1/3 of the mass of the spring will come. So omega n will be k by m plus ms by 3 root over. So here this is one example of Rayleigh's method. So let us stop here. In the next class we see another example of Rayleigh's method. So here